No, lo tengo. Sì. Vabbè, in caso non funziona, insieme il cambio.
Okay, so hello, everybody. It's a pleasure for me to introduce you Santi Cassisi. Well, for the few of you that don't know him, probably the youngest ones, because Santi has been visiting us for the last more than 20 years. And so he's an old collaborator, an old friend. And he has collaborations with many people at the IAC and is willing to expand his pool of collaborators. Santi is the leader of the Basti library, which a few years ago, and based with funding from Severo Ochoa, was extended to become the Basti IAC library, which is very important. And Santi is extremely prolific. He has more than 300 referred papers with 25,000 citations, more than 70 papers with 100 citations. So this is quite impressive. And on top of that, has two books at the, let's say, a university level for teaching. So I leave you with Santi, and thank you for coming.
Okay. Good morning. Thanks for coming. Let me firstly thank Karma for this nice introduction, and also I would like to warmly thank Anne Scorza and Karma for allowing me the possibility to stay here, thanks to the funding provided by the Occidente and La Caixa foundations. So what is the aim of this talk? The aim of this talk is to provide you some information about one stellar model library that has been largely developed in collaboration with some person working in this institute. So it is a pleasure to name this library as Basti at IAC, and I give you some information about that. And I discuss in particular what is the present status of this library and what would like to do in the near future, maybe. And since I don't want to bother you with too many details, and I think it is also interesting for you. One other purpose of this talk is to make a comparison with doesn't work, perfect. Okay, but okay, don't worry. With what nothing is okay, because I tested before and it was working. Yes, sorry. The idea is also to perform some comparison with the most used stellar model library that you can find in literature. And I'll try to provide an as much as possible unbiased comparison, because I am the producer of one of these libraries. So in some sense, I am biased for sure about this. So let me start from scratch for people that is not fully aware what does it mean to compute a stellar model. What does it mean to model a star? To model a star means to put all together different ingredients that we need to use for cooking a stellar model. There are many ingredients that we need to use. For sure, we need to use an evolutionary code in order to solve the stellar structure equation. We need to fix a surface boundary condition for closing from a mathematical point of view, the set of equations. And also we have some issue about numerics. Another important piece of information that we need to use are the physical inputs, equation of states, law of opacity, Lagrange reaction rate, and so on. Actually, I don't enter in any detail. So if someone of you has some curiosity, please ask me. I don't want to enter in some specific detail about anything in this context. Another important ingredient is how we manage the mixing of stellar matter inside the stars is crucial, is a fundamental ingredient that we need to use. They are mixing during the core hydrogen burning phase in intermediate mass stars, but there are also some crucial mixing process occurring during the core helium burning phase as semi-convection, breaking parts, and so on. And also we need to account for microscopic mechanisms like atomic diffusion and radiative levitation that are very important because they impact not only on the evolution lifetime, but it also impact on our capability to properly compare stellar model with spectroscopic evidence. And also there are some other ingredient that I like to name as infamous unknown, because after 50, 70 years of stellar evolution, we still face with significant problem about this, as for instance, the efficiency of mass loss in stars of different mass, what is the efficiency of the dredge up during the asymptotic giant branch phase, and also what is the correlation between mixing and peculiar chemical abundance at the surface as carbon enhancement, oxygen enhancement, as we observe in evolved AGB stars. And also there are something that is usually, at least it was commonly ignored until 10 years ago, that is the presence of magnetic field rotation in stars. Nowadays, we can no longer neglect the presence of this physical process in stars if you want to properly understand some detailed empirical evidence coming, for instance, from astero-seismology and high-resolution spectroscopy. So we need to put all together if you want to cook a stellar model. And I have to say that some of these physical inputs are more crucial than others. For instance, because some of them, like the opacity, the energy generation coefficient that is related to the evaluation of the nuclear cross-section, enter directly in the solution of the stellar structure equation. So they really have a huge impact on the model that you obtain. And also there is, of course, the equation of states. And what does it mean to compute a stellar model? When we put all together this ingredient and start the machine, what we obtain for each stellar model, for any specified mass, chemical composition that you can provide me, for which you are interested, our code produces a sequence of models that are also a sort of snapshot in time of the evolution of a star. This is the sequence of data that we obtain on the screen. That is with the time, the luminosity, the effective temperature, all the internal physical property, density, temperature, whatever you want, change with time. And we can collect this information, and so I can give you a detailed description of what is the life of that specific star, starting from the pre-main sequence up to the most advanced evolutionary stage. And what are the output that we obtain? We obtain evolutionary lifetime, that is the age of the star in a different evolutionary phase that you can compare with star counts. We obtain bolometric luminosity, effective temperature, and mass. And the actual mass is commonly different than the initial one as a consequence of the occurrence of mass loss, also in single stars. And when you put together this information, you obtain surface gravity, effective temperature, and so combining this information with accurate synthetic or empirical spectral library, you can obtain magnitude, color, spectral indices, surface brightness fluctuation, and many other things that you can apply in different fields of research in astrophysics, okay? From the local field star to very far galaxies. So the point is that indeed all this information that are provided by stellar model are crucial for many, many topics of research, okay? So the point is in the market, you have many stellar models, okay? You have several libraries, and I'll mention some of them in the following. So the reason is, why a new stellar library? Okay. And what I did, since we are in the modern age, I asked it to ChatGPT, and I say, but stellar model is really important today? And this was the answer that I obtained. And I say that the stellar evolution library serves as a critical theoretical foundation. Indeed, the stellar models are very important, and the insights derived from this model are indispensable for the interpreting observational data. So we can be happy, we are, I'll say, authorized to continue working in this field. And let me say something that is important. You can use stellar model in different environments, in different fields of research. The most crucial information that comes from stellar model is the age of the star. There is no way you cannot obtain the age for any star without using stellar model. The people that say that they can date the stars without using model are completely wrong and false. Okay, there's just one possibility to obtain the age of stars independently of a stellar model, but you can apply this just for a bunch of stars, 10 stars, 50 stars in the whole universe, and they are the stars for which you have accurate measurements of the radioactive element. In this case, you can date the stars taking into account the decay time of the different radioactive isotopes, but this you cannot do too much with 15 stars in the universe, okay? So starting from this point, let me say, okay, we have different library. As when we go in a car shop, we need to decide what kind of car you would like to have. And what are the criteria that we need to apply, according to my belief, in order to choose a library? For sure, one is basic, updated physics, okay? You want a model that account for the best physics you can. For sure, homogeneity, and is something important that is usually ignored by people, and I'll come back on this point later. Completeness, you would be happy to have a library that covers all range of mass, all chemical composition, all evolutionary phase. This is not always possible, at least in the past it was not possible. Accuracy, for sure, you need a reliable model. User-friendly is something that the importance of this, you discover this when you want to put a stellar model inside your code, okay? I'll say something later, but not all the stellar library have this facility. Sometimes you need to use stellar model library, and to put them in a synthetic code, in a galactic evolution code, whatever, can be very complicated and extremely time consuming. And also, I think something that is important is also the possibility to obtain from the team producing that specific library, specific model on demand, okay? You are interested to study these stars, this specific mass, chemical composition. Can I have a stellar model specific for that star? Sometimes this is impossible, okay? But this is not always the case. Okay, so what is BASTI? BASTI is a last release of a stellar model library that we start producing about exactly 21 years ago. The first library was produced in 2004, was published in the paper in 2004. And this is the update of that library. This project started in 2018, involving some people working here in the IAC, as Sebastian Hidalgo, Antonio Parisio, and many others. And this is the link from where you can connect. This is the homepage of the library that you find on the web. And entering in this web page, you find the complete updated library. Let me spend a few words about this library. This library is complete in the sense that it's covered a very wide range of mass, starting from the minimum mass for hydrogen burning, 0.1 solar mass, up to 15 solar mass, okay? They cover almost all evolutionary phases relevant for the star, from pre-main sequence to white dwarf cooling sequence, or carbon ignition, or thermal pulses phase for intermediate mass stars. This is the most complete library that you can find in the market concerning the number of metallicity. We have 21 metallicity, and we are continuing increasing the number of metallicity when the people ask us for additional grid point. We have, and this is a unique case in the market, 3 different heavy element distributions: solar scaled, alpha enhanced, and alpha depleted. Solar scaled is very important for the solar neighborhood, alpha enhanced for the most metal poor system, and alpha depleted can be really very important for an appropriate a very accurate tracing of the properties of stellar population in local group dwarf galaxy. And it's based on the most updated physics that we have at the time we started producing the library. The outputs, what are the one? Stellar tracks, stellar structure that you can use as input for astero-seismic analysis. We provide model in the format suitable for almost all common code for studying non-radial pulsation in star, isochron, synthetic Magnum diagram, and whatever you want. Just to give you some number, one of the motivations, let me say, for starting this collaboration between the BASTI team and the IAC was motivated by the first Severo-Ochoa call or review. One of the requests of this was that this should, any work related to the Severo-Ochoa should enhance the visibility of the institute, increasing the number of citations and so on. And I think that we reached this target because the papers that are related with the BASTI library publication are more than about 3,000 so far, and about 35% of these citations are related to the 3 papers related with the last release of the BASTI library, the BASTI IAC. And we have collected so far, concerning only last release of the library, about 100,000 connection, let me say, downloads of stellar model, isochron, or realization of synthetic or magnetic diagram. Now, let me make some comparison with the other car in the shop, okay? So the library that I selected was our first release, the past, BASTI, that is still commonly used by many research groups. The last release, BASTI IAC, and here you see what are the references related to this library. The well-known and commonly widely used PASEC library, that is the Padua Trieste Stellar Model Library, and also the famous or infamous MESA, the MESA database. The database that is based on the use of the MESA code, and that's the reference. Okay, so let me say that among this library, the most commonly used is the PASEC one. Okay, and this is there is a historical reason for this. It has to be acknowledged. The Padua people was very intelligent and brilliant. A long time ago, more than 50 years ago, they decided to produce the first extended library of stellar model. It was a unique case in the market. We were working at the same time on stellar model, but we were focused on specific topic. We had not in mind to produce a big library. So we started about this only in 2004. Okay, so they were the first to enter in the market, and for sure, who first arrived with the best sellers. So MESA is the most recent library. There are other libraries in the world, okay, but they are not so extended. They are not so useful for many purposes as those four libraries that I selected. MESA is the last one. It's based on the use of the MESA code, the MESA acceleration code that was elaborated by Baxter. And in my sense, and after I explain the reason for this, MESA is an opportunity, but it's also a problem. And I'll tell you what is after the problem. Let me now make some very rough comparison between the different libraries, okay? But just to give you an idea. One of the first ingredients that you need to choose when you compute a model is the heavy element distribution. In this last 20 years, there has been a big fight. What is the most accurate solar scale heavy element distribution? This is the so-called problem of the solar metallicity. What is the real solar metallicity? This is the Grevesse-Soal distribution, the so the Asplund, Grevesse-Soal, and others, and the last, one of the most recent KV determination. The problem is in particular in the estimation about carbon, nitrogen, and oxygen. There are significant difference among the different evaluation, and this impact a lot in many astrophysical issues. The first one is that the most recent not the most recent. The evaluation provided by Asplund in 2005, revised in 2009, and after in 2015, is in sharp contrast with any helio-seismological constraint, in particular the capability of stellar model to reproduce the solar sound speed profile. With the KV 2011, the situation improved a lot. Okay, so what is the situation? The different library rely on different mixture. The first one, the BASTI first release, was based on Grevesse and Noel. The most recent one is based on KV, that we think still is very reliable. PASEC is based on KV, but MIST was based on Asplund, 2005, okay, revised in 2009. And this mixture, the one suggested by Asplund, is highly, you cannot use it. It's clearly wrong, okay, for many reasons that I have no time to discuss. And they recognized this, and a few years ago, they recomputed again their library using the Grevesse-Soal that is quite similar to KV 2011, okay? So, concerning, just to give you an idea, the choice of the heavy element distribution is not something trivial, okay? Also, if you fix the physical framework, use always the same equation of states, or basically blah, 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 just only changing the mixture, you can obtain significant difference in the age of the star that you are analyzing. These are tests that we did in the framework of the Plato mission preparation work, and simply just to explain, just only changing the heavy element distribution for this mock star, we can obtain difference in age, simply changing the mixture from Grevesse to Asplund and KV 2011 of about also 10%. That is something not negligible, okay? Something that has to be kept in mind. Concerning the input and the other ingredient, the evolutionary code. Concerning the evolutionary code, numerics, boundary condition, and so on, I think that all libraries are good because are based on reliable stellar evolution code. Concerning the boundary condition, that is how we fix the solution of the stellar structure equation. Here the situation is a little bit more complicated. And let me say that in some sense, the worst choice is the one adopted by the Padua group, because Padua rely on the gray thermal stratification that we know is something that should not be used. Okay, this is a mystery for me. The reason for which they continue to use this way to fix the boundary condition. They also use a calibrated Phoenix boundary condition for the very low mass regime. That is something that I don't like really too much. I would like to say, for people that work on the comparison between empirical data and observation, that is not a trivial issue, because when you fix the effective temperature scale of the stellar model is strongly dependent on how you fix the calibration of the mixing length, but also on what are the boundary conditions that you adopt. When you perform the calibration of the mixing length using the solar standard model, you are sure that your model, different model overlap by construction at one solar mass, solar metallicity around the main sequence, okay? But this does not guarantee you that the same good agreement is also obtained, is also along the Reggian branch. And you can have difference of the order of 100 degrees simply changing how you fix the outer boundary condition in your model. So in my belief, concerning parsec and also MIST, we cannot be very confident about how they fix this boundary condition. Concerning other physical inputs, concerning the equation of states, all equation of states use the same equation of states, the same radiative opacity, so we are happy. Concerning conductive opacity, in this case, the worst situation was the one based on our first release, BASTI, because at that time, all the stellar models were based on not appropriate conductive opacity. In 2007, myself, in collaboration with some other group, we provided a new conductive opacity, and we adopted this new conductive opacity in our library, and this was also adopted by Padua group and MIST, so we are now all very happy. Concerning the nuclear reaction rate, all stellar models are based on the more or less the same nuclear cross-section that are the most updated that we are currently available. So we are a bit happy about this. Concerning macroscopic process, that is the treatment of mixing in different evolutionary phase, overshooting is accounted for by all stellar model library. Overshooting is another crucial point when you compute a stellar model, because these usually affect the evolution lifetime and the age of star in the regime of star, for star that develop a convective core. That means for star with mass larger than 1.2 solar mass, more or less. And different approaches are used to fix the boundary condition. How to extend the size of the convective core behind the classical Schwarzschild criterion, okay? You can use step overshooting that correspond to this approach. If you have the canonical convective core, you increase by a bit the size of this core by this quantity, where lambda is a free parameter, HP is the local pressure sky height. Okay, you can do also different assumption about if the mixing affect or not the thermal structure. And indeed, in the case of Basti and Padua, parsec, we use this approach with this value for this free parameter. Parsec was based initially on 0.25. Recently, they have revised to exactly the same value that we use. So in this context, parsec and Basti are more or less the same, not exactly the same, but more or less the same. Concerning MIST use a different approach. That is this one. They assume an exponentially decreasing efficiency for the overshooting. It is treated in this way, and so in this case the value is different, but they have also a free parameter that they need to calibrate, and they use this value that is more or less consistent with a value for this value lambda in the case of step overshooting, more or less consistent with the value that they have. So in some sense, the treatment of overshooting is more or less the same, but the effects are not the same, okay, in stellar modeling. So another point that you have when you treat account for overshooting in stellar model is how to decrease the efficiency of overshooting when you approach the mass regime for stars that have a radiative core during the core hydrogen bonding phase. You have to decrease this for physical reason, and you can decide to use a sort of ramping between the stars that do not develop convective core up to a complete efficiency overshooting for stars with mass larger than about 1.5. You can use different prescription on how to manage the treatment of convection in the regime between 1 and 1.5 solar mass, and this is critical, because the approach that you use impact on the morphology of the isochron. These are the same isochron, the same age, 5.5 billion years, same chemical composition, but you see that the shape change a lot, simply changing how you treat the efficiency of overshooting in this critical regime between 1 and 1.5 solar mass. We adopt, in the case of BASTI, we adopted this ramping solution, a linear increase of the efficiency overshooting that was not very, very accurate, okay? In the last database, we used a different approach that is based on physical consideration related with the evolution with time of the convective core during the core hydrogen bonding phase that has provided a very good agreement with different empirical benchmarks as eclipsing binary, open cluster, and so on. In the case of Padua, they use something completely different. They fix that the overshooting has to always increase from 0 to the maximum value they adopt with a fixed mass range that is whose width is about 0.3 solar mass. This is something that my belief is not fully appropriate, but this is the politics that they decide to adopt, something that should be investigated. I don't see any comparison of their isochron with the open cluster and eclipsing binary to test the reliability of this approach. In the case of MESA, they claim that the use of a diffusive approach for the overshooting do not require any treatment of this problem, something that also has not been tested or verified so far. Okay, concerning superadiabatic convection, all models adopt more or less the same approach. Concerning semiconvection, I have no time to discuss. Semiconvection is a critical mixing process that occurs during the core hydrogen bonding phase in all stars, in particular in low mass stars. Okay, stars that typically characterize the central bonding phase in stellar population older than about 6-7 billion years. Okay. You have to manage the appearance of a discontinuity in the gradient, and in the case of BASTI, the both release and missed semiconvection is accounted for. Parsec does not account for semiconvection, and this is quite critical because depending on how you manage the existence of this discontinuity, I have no time to enter in detail. You can, for instance, we use in BASTI and BASTI IAC an approach that takes into account the need for avoiding this discontinuity in the gradient, okay, in a very appropriate way. Parsec decide to put overshooting, okay, so they don't take care of the physics of the process. MESA use a diffusive mixing scheme, but whatever is the mixing that you use, this has a strong impact on some prediction coming from the model, as the lifetime during the core bonding phase, the extension of the blue loop that affected the evolution of classical CFITs. And so when you compare with the data for classical CFITs, this is something that enter into the game. What is the luminosity of the asymptotic giant branch clamp? The carbon-oxygen profile in white dwarf has a very dramatic effect as well. I don't discuss this in order to, I have no time just to say. Breaking pulses. Breaking pulses is a discontinuity, is an instability, sorry, that occur near the end of the central bonding phase. It's something that should be taken into account, and actually neither Parsec and MIST do not take into account for this process. This is probably accounted in both BASTI and BASTI IAC. Concerning rotational mixing, that means that the possibility to account for rotation in stellar model. Indeed, my library in the first and in the latest release do not account for rotation, when Parsec and MIST account for rotation. Actually, just 1 month ago, we updated our evolutionary code. So we now include also rotations in our model, but this model have not been yet produced, so they are not in the library, okay? But I would like to say something as a takeaway news. When we use a model accounting for rotation, the parsec, MIST, and in the near future also the BASTI model, please do not trust them. They are completely wrong. I started computing model with rotation, and I have to say that the capability of this model to produce something that is realistic is practically similar to zero. In the sense that there are so many free parameters that you have to account for that the model loses completely any predictive properties, in my belief. Okay, so you can use as a guideline to understand something, some evidence, but not to properly interpret what you see. Okay, and for instance, just to give you an idea of how large is the uncertainty that we have concerning rotation. This is for a comparison between the MESA and Geneva model. Geneva is another library of stellar model that accounts for rotation since many, many years. This is the ratio between the evolution lifetime for rotating model compared to non-rotating model. Okay, one means that the time is the same, and it's increased as a function of the mass. These are the Geneva model, and these are the MESA model for different assumptions about the free parameter that I mentioned before. You see how dramatic is the difference. Okay. So, no way for rotation. One problem with the rotation is that, and I go fast here, is that all models are not able to properly interpret or predict the extraction of angular momentum from the inner part of the star. Okay? So all models, MESA, parsec, also our model, are not able to extract angular momentum from the inner part and remove this from the star. We are working in this direction because it is clear that we need to include in the model additional physical processes as internal Galilei wave, magnetic field, mass loss that could help in extracting and removing angular momentum. But once again, I have to say, if we do this, we introduce other additional free parameters. Okay, so keep in mind that there are no perfect models concerning rotation, maybe also no perfect model about anything, but in the case of rotation is really a nightmare. So concerning diffusion, diffusion is, I refer to atomic diffusion and relative levitation. All library, but BASTI, include nowadays atomic diffusion, okay? In the case of the old BASTI release, it was not included. And, but the point is, how we include diffusion is reliable. Let me say that not too much, in the sense that we know that in order to account for atomic diffusion and relative levitation, we need to properly evaluate some diffusion coefficient that are this quantity that appear here in the case of diffusion, and in the case of radiative are this coefficient here. Okay, the evaluation of this parameter is quite complicated, depending also on quantum physics and so on, blah, blah, blah. And so the uncertainty with which we know the value of this coefficient is about 10 to 20%. So our capability for all group to predict properly the efficiency of diffusion is a little bit limited. And also there is another problem. The problem, roughly speaking, is that on theoretical ground, we know how the efficiency of diffusion changes when you change the metallicity, the efficiency of convection, whatever you want, the mass of the star. But when we compare our prediction with the evidence coming from spectroscopy, for instance, of galactic orbital cluster, in which we can measure the surface abundance at the main sequence turn-off and on top of a giant branch, where remember that the effect of diffusion are larger for stars that are at the main sequence turn-off. When the star moves to the red giant branch, due to the occurrence of mixing, the initial surface abundance are restored. Okay, so measuring the difference, we can evaluate what is the efficiency of diffusion. And indeed, all stellar models that are in the market overestimate the impact of atomic diffusion. In order to do this, we need in some way, in some artificial way, to inhibit the efficiency of diffusion. Okay, and this introduces some additional free parameter. Now, let me talk about, the updated physical inputs. We can say that more or less we are the situation that I mentioned before. Concerning homogeneity, all the BASTI model and BASTI IAC model have been computed with the same physical input and exactly the same evolutionary code. In the case of parsec, they changed the version of the code and some other ingredient on flower. while producing the library. In the case of the MIST, that is the main problem that you have with MIST. In the case of a MIST, MESA is a public code. Okay, so anyone using this code is able to change everything inside the code. Okay, and so you are never sure that the model that are on the library that have been put today and that will put tomorrow have exactly the same physics, the same choice about the physical quantity and free parameter that enter in an evolutionary code. Okay, I've been the referee of many papers of MESA group, and what they claim at the beginning is the model presented here has been produced with the code number version 204778. Okay, for me, I said this doesn't mean anything. This is an information that is useful only for people that use the MESA. But for people that is a potential user of the library, you cannot say what is the release of your code. You have to exactly explicitly say what is the physics that you're using, the physics, the choice of the free parameter, whatever. So in some sense, the MESA is not so homogeneous as they claim. Concerning completeness, indeed, the most complete library, in my belief, are BASTI and MIST. Okay, in the case of Parsec, there was something missing. They are now including some additional model, but when I did this slide, I forgot about this. But there is some problem concerning completeness. In particular, for instance, in the case of Parsec, they provide only solar-scaled model. There is no alpha-enhanced model, no alpha-depleted. In the case of MIST, now, just I think a few months ago, appeared a paper where they publish also alpha-enhanced model. But until 4 months ago, they provided only solar-scaled one. Concerning the accuracy, okay, I think that the BASTI IAC model are quite more accurate than the BASTI one. Concerning the Parsec and MIST, since they are not my model, I don't want to say too much, but I think that additional work should be done in order to test the choice that they did when computing the model, comparing this model with open cluster, eclipsing binary, astero-seismic constraint, and so on. I think that some work in this direction should be done. Concerning the user-friendly, okay, now I can spend something about it. Concerning user-friendly, I think that the most simple library to be used by any potential user are BASTI and BASTI IAC. For the simple reason that all the files that you download for that web page have exactly the same format, the same number of lines. You can find any specific evolutionary stage always at the same line in all evolutionary tracks, in all isochron, and whatever you want. So there is a very huge homogeneity in the data file that you obtain. So it's very easy, like a hot swap changing of an hard disk in a computer, to include the BASTI and BASTI IAC library in any code that you can try to use. The same does not apply at all for Parsec. The isochron in Parsec have a different length, the equivalent point, the crucial point along the tracks in the isochron are in different line in the isochron, as they explicitly say. So it's not so easy to be implemented in a library, but this can be done. Concerning a MIST, I have to say that I have been never able to open a MESA isochron for the simple reason that they provide 95 columns. Okay, I have a 45-inch screen in my office, and I have some difficulty in moving 95 columns. Okay, but just not joking, but the situation is more or less this. So concerning the possibility to obtain specific model on demand, we have always provided this. In the case of Parsec, I don't think that is possible. I know that people asked to receive set of isochron for specific metallicity, and they have never received an answer, or maybe if you are friend, you receive. But in any case, there is no direct access to this possibility. In the case of MIST, I think that is completely impossible. You can download the code and compute yourself the model, but they do not provide an official release of the grid. Let me say that BASTI IAC and Parsec are the library that provide you model in almost all photometric system. Okay, this is a very good point of strength for Parsec. They started with this facility to provide model in any photometric plane. It was something that they made a very good job about this, and they have a very nice interface concerning this. Okay, we can do this in the sense that if you provide me any specific photometric passband, in a week we provide the bolometric correction, so we can transfer the model in the photometric system that is of interest for you. Okay. So good. We made some comparison between our model and data. These are for open cluster, Gaia data for Gaia parallax for the cluster HIDIS in different photometric plane. And you can see that the vast IAC model works really very well in different photometric system. This is one very spectacular, this is the most near galactic globular cluster, very metal pool cluster, NGC 6397, and you see how the finest portion of the main sequence is really very well reproduced by this model, and so on. Now I just wanted to show you some application of the vast IAC library. One of these applications is related to the work that is done in IAC. One is this. This is the comparison between the Basti model and the Gaia golden sample. The Gaia golden sample is a sample, very large star, for which there is exists a very accurate determination of metallicity, effective temperature, and gravity. You see that the error that are listed here are actually very, very small. This allows you, if you make some selection in metallicity of the star, to make a sort of a direct comparison in the Espon-Russell diagram of the Kiel diagram, gravity as a function of effective temperature, between the model and the observation. Okay, so it's something, it's a very strong constraint for the model because you know very well the metallicity of the star. Okay, and this is what has been done by Alejandra Recio Blanco in collaboration with the other person of the star. These are selections, star selected using bin of 0.1 dex in metallicity, and the agreement between the different stellar model, Basti model selected according to the metallicity is very impressive. The difference in effective temperature along the regime range was 50 degrees. Okay, so the comparison once you select the observed star in metallicity, a very, very teeny metallicity bin, the difference between the model for that, the Basti model for that metallicity and the stars were 30 degrees. The MIBD is almost nothing. Okay, so the agreement was very good. Another project in which Basti IAC together with Parsec is extensively used is a project of Galactic Archaeology, whose aim is to recover the process of assembly of the Milky Way. In this game, in the game of Galactic Archaeology, the crucial information is the age. Okay, and as I said before, age is coming from a stellar model. And here, this is a project whose leader is Carme Gallard. For the Spain part, I am the responsible in Italy for an equivalent project similar to some say correlated project Kronos that is funded by the Italian Ministry for Research. And the idea is to compare empirical absolute color magnitude diagram obtained thanks to Gaia data with the appropriate color magnitude diagram in order to recover the age metallicity distribution of a star belonging to the different subpopulation of the galaxy. We have obtained, I think, quite important result in this field, and I would like just to, the idea is the one that is at the base of the color magnitude diagram fitting, so you compare the observed color magnitude diagram with the synthetic one, and reproduce the observation via a linear combination of simple stellar population that you extract by properly comparing theory with observation. This has been extensively used for local group dwarf galaxy in the context of the LC project at the IAC, and now is applied thanks to Gaia also to stars in the Milky Way. Okay. And I would like just to show you one of the results that I think is very important. This is based on a paper submitted by Emma Fernandez Alvar and collaborators, and is the difference in the age metallicity relation between thick disk star and thin disk star in the galaxy. And what we obtained with a very high accuracy is the fact that there is a transition in time between the formation of the thin disk with respect to the time of at which the star formation stopped in the thick disk. I don't want to discuss, but just to say that in order to make this kind of study, you need a reliable stellar model library, but you don't have to use just one library. We are doing this work also using the Parsec library in order to assess what are the systematic in the result associated with the use of different stellar models. Okay. So As a byproduct of this kind of analysis, we obtain also metallicity distribution, and this has a strong advantage with respect to spectroscopical survey for the simple reason that our analyses are not affected by spectroscopical by selection bias, but the point is how we can trust the reliability of the metallicity distribution that we obtain when comparing Gaia data with the stellar model. And we can do this comparing our estimated metallicity distribution with the one obtained by different survey. And you see the comparison. I don't discuss this in detail, just to say that the agreement is very good, okay? But the point is, this metallicity distribution, for instance, depends on the set of stellar model that you obtain. These are the results that you obtain when comparing with the spectroscopical survey, the result coming from the BAST IAC library. If we change the library, okay, we won't discuss this, the situation is this one, okay? This is the comparison between the metallicity distribution obtained with BASTI and with PARSEC compared with the golden sample, with the, is the golden sample, is the Gaia catalog, the nearby star catalog, okay? And you see that in the case of the BASTI, the agreement is quite good, but I think that this is quite more evident here. This is a comparison with the spectroscopical data by Fuhrman and collaborator 2017 for stars that are within 25 parsec around the sun, okay? And this is the green line is BASTI, okay? The dashed line is parsec, and the agreement between BASTI and the spectroscopical data is really impressive, okay? And there is an offset of about 0.2 dex between the two metallicity distribution. I have the suspicion that this is due to the different effective temperature scale between the BASTI as a model and parsec one, but something on which we are working. So the future, I'm almost finished. For sure, we continue to update the physics that we are adopting in stellar model. This is a never-ending story. It's more than 55 years that I do this job, and I'm continuously updating the physics in the stellar model. For sure, we would like to create new synergy, new collaborations with people working here at the IAC. We, for instance, I think that we could find a strong point of interest with the astero-seismic group. I had several discussions with Savita and Paul along these days, but I think that something that will be also very important is to collaborate with the group working in the field of brown dwarf and massive exoplanet. As I said, the BAST IAC stop at the minimum mass for hydrogen binding, 0.1 solar mass. But indeed, we can reach the regime of brown dwarf and massive exoplanet. We have the physics that we require to do this, appropriate equation of states, opacity, and so on. Another possibility is also to extend the library stellar model to mass larger than 15 solar mass, as we currently did, reaching to 25, 30, 40 solar mass. In the hydrostatic phase, for sure, we cannot follow the explosive phase of a massive star. What is the problem? We have the code can be adapted to compute this model. The main problem that we have is manpower, okay? The BASTI team is really very small, and we cannot work on all the fields. So we need to make some choices. So anyone that want to collaborate, I'm very happy to collaborate with on this subject or whatever you are interested in which the model can really be applied. So final remarks. I have no final remarks. Actually, I asked it to ChatGPT. ChatGPT, please, can you tell me what is the best library? You said no, the best library. What do you think about the BAST IAC? It is what ChatGPT said, okay? I don't read it, but in some sense, he's saying that we are good enough, okay? So I am happy saying in particular this one, the responsiveness underscored that the value, sorry, no. the value that the researcher place on having access to state-of-art stellar evolution model indicated. There is a strong interest of the community in regards to the BAST IAC model. So I think that we can be, all the BAST team is very, very happy. So maybe we are the best, the BAST.
Questions? Thanks a lot, Santi, for this very comprehensive talk where this a lot of information. Yes, no, it was great. Thanks. So I totally agree with you on the fact that you are saying that to get ages, we need to have stellar evolution models and the best that we can. But you didn't mention, I mean, it's kind of uses stellar models, but we are trying to have like these rotation age or magnetic activity age relations using clusters or and this way we can have ages without using the models at the end, even though we used the models. So do you have any comment about this?
Different methodology you can use for dating the star, the chronology, the intensity of the magnetic activity star. It's very important to use it and compare it in order to have a different estimation of the age of star belonging to different evolutionary stages. But all basic calculations, all the methodologies are very linked to one another. If you want to calculate gyrochronology, you have to start taking the cluster, for instance, you take the global cluster mentioned in the answer, for instance, the sequence of and then you calibrate this relation. You also have the United cluster with different rate, you measure the rotational rate and compare. So I think this is methodology that has to be applied. We need to want to in my project was to compare the age data from different methodology in order to put in a certain different way different age scale. Okay. The people that don't take into account that the different methodology provide different age scale. This should be normalized to a common age. Okay. The fact in any case, this is the main point. So for sure, I think that my suggestion is that this calculation should be used on view of difference around the lab. The model are not best, but they are not best model in mind. Okay. Each model has its own advantage and shortcomings. So comparing different something from different lines alone economic effect in the system. That maybe the moment of the
Thank you, Santi, for a very comprehensive talk. I want to ask you about the ignition of helium at the tip, because some models have problems there. Did you test, or did you also compare the different model libraries and codes, how they perform on the ignition and where stars settle on the red clump?
What do you mean as a different model have problem? In the sense that we know very well what is the physical behavior of what is occurring before the reaching of the condition for helium ignition in low mass star. I think that you are referring to stars that develop the helium ignition via a thermal runaway or via an helium flash. So we know this very well. And we know also what happened in this star once the helium ignition starts. One problem that we had in our mind was, since the thermal runaway is a really very violent process, in the sense that when a star develops a helium flash, indeed for a few seconds it produces the amount of energy that is larger than one produced by a galaxy for a very short time, but this does not destroy the star, okay? The star remains in electrostatic equilibrium. We try to say, okay, maybe our 1D model, because all the models that I mentioned are one-dimensional models, are not accurate enough. But luckily enough, a few years ago, we have produced some 3D model of star experiencing the helium flash. They follow it in detail. It was very curious and was lucky that indeed there's a 3D stellar model predicted that, for instance, just to mention something, the evolution of the convective zone that develop inside the star at the point where the helium burning starts, that is not a central burning. At the beginning, the burning starts in an off-center shell due to condition related to electron degeneracy and so on. Indeed, how the 1D model predict the movement and the location of this mixing zone is in good agreement with 3D. So there is no a big problem on this. So the model are accurate enough. What changed from one library to another library is the fact that the size of the helium core at the point when helium ignition starts change with the library, okay? For instance, just to mention, parsec model predict a different size of the helium core that I'm not able to understand when accounting for the helium abundance that they use, the physics that they use. There is something that I don't know, maybe also, for instance, the size of the helium core when the helium burning start depends a bit also the rezoning in the mesh point that you use in your code. I have no access to the Padua code, so I don't know what kind of rezoning they are using. But the numerics that you use, the assumption that you do can impact on that. But from the point of view of the physics, why and when the star reach the condition for the helium burn, the ignition of helium burning, and how the star move from this part, this evolutionary phase to the red clamp or horizontal branch, depending on the system that you are considering, we have not a big problem on that, let me say.
Okay, perhaps we should have a coffee on that.
Yeah, okay.
Hi, so thank you for your talk. I wanted to ask if there is any concern of how much do you lose for not considering the rotation in high rotating stars.
Okay, let me pose the answer in this sense. For galactic archaeology study, for instance, in general, for studying all the stellar population, that means a stellar population populated by star with mass below 1.5 to solar mass, the fact that we neglect rotation is not an issue. For the simple reason that rotation, and this is clearly evident from empirical data, is not so strong in low mass stars. So low mass stars are not so fast rotate. They rotate, but not so fast. And the rotational rate that they have has no significant impact on the evolutionary lifetime. If I compute one solar mass model, so the sun, okay, for rotation or for non-rotation, okay, for reliable assumption. For instance, if I take into account for the real rotational rate for the sun, the age of the sun, in any case also in advanced evolutionary phase, is not affected at all, less than 1%. Okay, so an uncertainty quite lower in comparison with other sources of uncertainty. When we go to larger mass, let me say mass larger than 3, 4, 5 solar mass, their rotation is critical because the rotational is very high, the rotational rate, and this impact on the extension of the convective core. So this impact on the evolutionary lifetime. But the rotation also in low mass star can be important. If you are interested, for instance, to analyze spectroscopical evidence, because the surface abundances of star, okay, can be significantly affected by the occurrence of rotationally induced mixing that do not alter the evolution lifetime because they impact the outer layer of the star, but they can change the chemical stratification that you observe. So if you want to understand and properly interpret some spectroscopical evidence, you need to take into account also for rotation with the caveat that I mentioned. But for galactic archaeology study, for studying, also for, I think, astero-seismic data analysis is not a big deal, the problem of the fact that we neglect rotation commonly.
Hi, Santi. Thanks for the talk. This is actually going back to kind of related to Paul's point. Did you look at the differences in the predictions for the tip at the location of the tip of the red giant branch between the different models and your updated models? Was there much variation? Like I'm thinking now in terms of distances.
Let me mention in my library. I say that when we moved from the previous Basti library to the new one big change was the use of more updated conductive opacity. Okay. Changing the conductive opacity for physical reasons that we can discuss, the size of the convective core, okay, the helium core at the helium ignition decreased by an amount that in terms of volumetric magnitude was about 0.1, 0.50 magnitude. That is not a small amount. And this, for instance, impact on the evolutionary lifetime in the last portion of the red giant branch evolution. And so this impact, for instance, on surface brightness fluctuation. The in the case of different libraries that use the same, for instance, conductive opacity, okay, when you take into account the possible difference in the initial helium abundance that you use and so on, you see that there are some residual difference that you do not understand. So you don't understand. I do not understand what is the physical reason that can still produce that difference in the helium core. Okay, and take into account that the size of the helium core at the tip of the giant branch impact dramatically on the luminosity of the tip of the giant branch and also on the luminosity of the core helium burning phase, because the dependence of the brightness of this evolutionary phase with the helium core is very strong. The derivative is about 4. Okay, so a change of 0.001 solar mass, okay, 10 to minus 3 solar mass in the helium core mass impact on the brightness of this evolutionary phase. In the difference in bolometric is about 0.1, 0.15, something like this. So it's something relevant.
Okay, thanks.
One last question. Yes.
Hi, I'm quite concerned by the atmosphere of stars, because in the end, this is what the info we get, except for stars with astero-seismic data, but for most of them is only the light from the atmosphere we get. So would you have a comment about your code, the homogeneity, a bit like you did about the connection, the homogeneity, between the atmosphere, because and your code, the continuity, and possibly with others.
Okay.
Would you mind commenting that?
Yeah. Okay. Let me say that the model atmosphere, the independent model atmosphere computation, okay, can enter in the evolutionary framework into different ways. One way in which they enter always is because the bolometric correction that we use for transferring our model from the Espen-Russell diagram to the different photometric plane are obtained convolving the photometric passband with the spectral energy distribution coming from model atmosphere. So it is fundamental, for instance, for self-consistency to use model atmosphere computation that are based on the same heavy element distribution that has been used for computing the stellar model. And the unique case in which this has been done is in the case of the Basti library, because one part of the team has actually the duty of computing model atmosphere with Kurit's Atlas 12 code, self-consistent with the heavy element distribution that we adopt for the stellar modeling. Okay, and this is not the case for the other library. In the case of the other way in which model atmosphere can enter in stellar modeling is via the boundary condition, because we can use a boundary condition coming from model atmosphere. Okay, this is a bit tricky in the sense that we decide, for instance, for star more massive than 0.5, 0.6 solar mass, to not use boundary condition coming from model atmosphere, for the simple reason that for this in terms of self-consistency, because the model atmosphere use opacity, low temperature opacity, and equation of states that are not fully consistent with the one that we use in stellar modeling. We were forced to use a boundary condition coming from model atmosphere in the case of very low mass star, M-dwarf star with mass below 0.4 solar mass, because in that case it would be physically wrong to use thermostratification coming from functional relation as the Krishnaswamy or Gray as is done by other group. So we did the best to be as much as possible consistent, self-consistent concerning with model atmosphere. But I think that a lot of work can be done in this direction from almost all stellar library, in the sense that we should try to improve as a lot of the homogeneity between model atmosphere computation and stellar modeling. I want to say also something different. In these last years, there have been big improvement in the computation of 3D model atmosphere, okay, as you know very well. 3D model atmosphere can provide very important information about the efficiency of convection in the superadiabatic layer, thermostratification. And we are doing the effort to try to implement this prescription coming from 3D model atmosphere in 1D stellar modeling in order to make them a little bit more reliable, let me say. So this goes in the direction that you suggested. To say.
I think we need to stop here. So let's thank Santi again.